Hi everyone. In this video, we're discussing problem number 429, N-ary tree level order traversal. It's a problem from Leetcode. So let's understand this problem statement. It's a medium level problem. The statement goes like this. Given an N-ary tree, okay, first of all, what is an N-ary tree? So with the help of these examples, we'll try to understand. We need to return the level order traversal of the node values, right? Not the nodes themselves, just the values of the nodes. Okay. So first of all, what is the meaning of N-ary trees? Check this example. Okay, example number 1. So one root node is given. Here it is the node with value 1. So typically in a binary tree, we will have 2 children at most. For any given node, there can be at most of 2 children, one left child, one right child. In the case of N-ary tree, that is not necessarily the case. You can have more than 2 children. It can have n number of children. Any given node can have n number of children. Okay. So for example, the root node here is having 3 children. They are the nodes with values 3, 2, and 4. And check this particular node 3. It is having exactly 2 children, 5 and 6. Whereas for node 2 and node 4, there are no child, right? So given this N-ary tree, we need to write all these node values in level order. So what is it? What is the meaning of level order traversal? You can check this example. You can see the output for this particular example. You see the root node itself is counted as level 0. And all the children of the root node, 3, 2, and 4 are counted as like level 1. And all the grandchildren of root node, that is 5 and 6 alone in this particular example, they are counted as level 2, so on. And we are not just writing all these node values in one list. You can check this. The output is supposed to be list of lists, right? It is not just list of node values. It is list of node values, right? So we will have a separate list for every single level. For level 0, it's a separate list. For level 1, it's a separate list, so on, right? So we'll check this one more example. Example number 2. The root node is the node with value 1. It has 4 children. They are 2, 3, 4, 5. And node 2 is having no child, whereas 3 is having 2 children, 6 and 7. 4 is having 1 child. 5 is having 2 children. And 6 is having no child. 7 is having exactly 1 child, 11. 8 is having 1 child, 12. 9 is having 1 child, 13. And 10 is having no child. And finally, the last level, 11 is having 1 child, 14, and 12 and 13 are not having any children, right? So there are like 5 levels here. Level 0 is the root node itself, and level 1 is 2, 3, 4, 5, and level 2 is 6, 7, 8, 9, 10, and level 3 is 11, 12, 13, and level 4 is 14. And like I told you, it is not just list of node values, it is list of node values. We need to have a separate list for every single level, right? So this is the objective. Let's head over to whiteboard in order to come up with a strategy to solve this particular problem. So the problem statement is N-ary tree level order traversal. I have just written down the first example given in the Leetcode itself, right? What are we supposed to do? In the output list, we are supposed to have this alone as a separate list, and then 3, 2, 4 as a separate list, and then 5, 6 as a separate list. Okay, so that is the meaning of level order traversal. This is a classic example of BFS algorithm, breadth first search algorithm, right? So let's see how to solve this. First thing is, we will have to initialize a queue. We have to initialize a queue containing the root node. Okay, so we are putting the root node in this queue list, right? And let's also initialize another list for output, which contains the nodes from different levels. So the output is a list of lists, right? So for now, let's just initialize it as a list. Output is for now an empty list. Now we are going to create a while loop. While queue, what is the meaning of while queue? In the sense, while this queue is non-empty, as long as there is at least one element in this particular queue, we will have to carry out the following set of instructions. So while the queue is non-empty, let's first capture the size of the queue. Size equal to length of the queue. And we're going to create another list in order to capture node values from every level. And this is where we are going to create another while loop. While size is positive, we are going to remove the very first element from this queue. That is why we even call it a queue in the first place, right? Whenever we are adding the element, we are going to add the element to the end of the queue, or as we call it, we enqueue. And whenever we remove an element, we remove the element from the front, the beginning of the queue, or we call it dequeuing, right? So we pop off the element from the zeroth, at the zeroth index. We pop off the element at the zeroth index, okay? So I call it the current node, or I simply call it the current, cur, is equal to queue dot pop at 0. In the sense, we are just popping off the element at the zeroth index. The very first element we are just popping off. Okay, so that is the current node. Now we are going to add this particular node to this level list, right? We are going to add this particular, sorry, not the node. We are going to add the value of this particular node to this current list. So level dot append of current dot value, right? After we include this particular value to this level list, we are going to add every single child of this current node to this original queue. And it can be written like this: for child in current dot children, queue dot append child. This time we are appending the node itself, not the value of the node. Please understand that when it comes to levels, we'll be appending the value of the nodes. When it comes to queue, we are appending the node itself. So once we are done with this, we are going to decrement the value of size by 1, which means we just apply this particular set of instructions till that size becomes 0. In the sense, till we exhaust all possible elements in the current level. Then we will have to append the level list itself to our output list. Outside this inner while loop, we are doing it. Okay, output dot append level, and then we will have to return this output. And in this particular problem, the only edge case we will have to worry about is there is a possibility that the root node itself is empty. So in that case, there is no root node at all, but our entire code will make sense only if there exists a root node. Okay, so in order to tackle that particular edge case, we are going to introduce this conditional statement. If root exists, then we apply this set of instruction. Else, if it doesn't exist, of course, we are going to return an empty list. Let's now head over to Leetcode in order to code it out and see how it is performing. So let me change it to Python 3. So this is our solution. If the root node exists, right, only then we are going to execute the code itself. Otherwise, we are going to simply return empty list, right? So if the root node exists, then we are going to initialize a queue containing that root node. And also we are going to initialize output list, which is for now an empty list, where we are going to append more and more list for every single level, right? And we're going to have 2 while loops. We're going to create one inside the other. So the outer while loop is this while queue, which means as long as this queue is non-empty, unless we have covered all possible nodes, we are going to execute the following code. Okay, so that is how BFS works. Okay, like level by level, we are going to traverse, right? So we create this variable size, which captures the length of the queue, or you can even call it the size of the queue. And then we are creating another list, empty list. We call it level. This is where we are going to add the node values of the nodes belonging to every single level. Okay. So while another while loop we are creating, while size is positive, we pop off the element at the 0th index, or in other words, we are dequeuing, right? So that particular element, we call it current, and we have to append the value of that particular element to this level list. and we need to append every single child of this current node to the main queue, right? So queue dot append child, and we have to decrement the size by 1, which means that we are going to run this inner while loop till we exhaust all possible nodes at any given level, right? And then we will have to append this level itself to our output, because our output is supposed to be list of lists, right? And then return the output. So let's now test run the code. Okay, it clears this one test case. Let's now actually submit the code to see how it clears all the test cases. Good. Our solution is accepted, and the time complexity is also pretty decent. 74% is pretty decent, pretty fast it is. But the memory usage is not that very good. It's not really efficient. It's just 16%. We should be able to do better than this. So we'll think about how to optimize this later. But this particular solution, I hope you all understood, and thank you for watching.